Awesome. Great to be here at AI by the Bay, and excited to be giving this talk. Really quick, just quick show of hands. I'm assuming everyone here is familiar with GPUs, right? How many of you have heard of kind of other types of chips or other types of architectures that are out there? Okay, handful. All right, so that's super helpful. And we'll go through everything. And I think there'll be plenty of things that we talk about more technical. Some that I think will hopefully help give everyone a base understanding of everything. Just as a really quick intro, my name is Vasanth Mohan. I've been at SummerNova for a little over a year right now. I lead developer relations as well as product marketing. And so day in, day out, constantly talking with developers that are building on our platform in our cloud and using our chips to build the next wave of AI applications and agents. The slide that I wanted to start with just at a broad level, and I had to actually update it earlier today, just because Google Gemini just released their latest model, is kind of just an overview of how AI models have been evolving over the last year. This is a chart from a really great analyst firm called Artificial Analysis, and this was they constantly keep updating these charts on their website day in and day out. But this was kind of taken as a snapshot from their Q3 2025 report. And what you see is that over the last year, there's been amazing exponential growth in these AI models. But as you start to look towards the right side of the screen, what you notice is that the intelligence, which is what is being measured here, of these models is starting to taper off. And you actually start to notice that all of them are kind of starting to converge around very similar levels of intelligence. We're not kind of seeing that same level of exponential growth in intelligence from these models. That's not to say that we're kind of in a bubble or anything. It's just that we need some sort of extra boost to improve the model performance and intelligence. And you're not just going to get that purely just from working with these models in single shot prompting. So really, I think the LLM intelligence is really just progressing incrementally now. What we saw this morning was Google Gemini released their own their model, but again, like in that chart, it's only really an incremental improvement. As I was on the drive in, I was just kind of listening into one of the talks from them, and what they were basically saying is they've kind of improved the tone, they've improved some basic agentic capability, the cost is a little bit higher, but could you still use the existing models that are out there in the world today? The answer is yes. And so what we're not going to be getting is that same level of intelligence exponential growth that we've seen in the last year. Instead, what we're starting to see as the trend that is emerging is that efficiency is more critical than ever. And that efficiency can come from a wide range of areas of the stack, all the way from the chips, all the way up to your agentic applications and how intelligently you actually use these models. And when we're talking at the chip level, one of the trends and headlines that you might be seeing is that we're at this inflection point in terms of the amount of power that's being constrained in primarily in the US, but you see this across the globe too, and that we need more power to run these data centers and run all of these workloads. So a metric that you might see that's floating around is the number of tokens per watt. And I think it's a decent metric for measuring the challenge that we have at hand. But I think there's an actually better metric that we were part of a report with Stanford just talking about this. And what they've described in their paper, which I definitely recommend anyone takes a look at and reads, is this metric called intelligence per watt. And I think a very similar metric that you see the CEO of Microsoft, Satya Nadella, talk about is tokens per dollar per watt, which is kind of effectively the same thing. But to really summarize this, what intelligence per watt describes is how much intelligence you can get out of the model for every watt of power that you actually end up putting into the system. And what you can see in their papers, they were looking at what's happening with local LLMs, what's happening in the data centers, to really help address this problem. And they've come up with some very innovative ways to tackle that, whether that's using local LLMs for certain tasks where you can have much better efficiency, and use the data center for some of the bigger models and agentic tasks that these smaller models that don't fit on laptops could actually that actually need to be run on those servers. And so that's where they came up with the metric as a means to really help us quantify the fact that we need to start optimizing for this to maximize the amount of intelligence that we're getting in the data center while we're power constrained. And taking power and building up power takes a long time. I mean, that was on the BG2 podcast, that's what Satya Nadella was talking about, is the fact that he has all of these GPUs. He has nowhere to actually go and plug them in. He doesn't have what he refers to as warm shells where he can put the power in. And so that's how much of a problem we're at in terms of the economies of scale that we're getting at with AI. So that's, and largely that kind of comes down to some of the efficiencies that you get with GPUs. They're really great for a lot of training use cases, but when you're looking at AI, there's a lot of different other types of use cases that are out there, especially when it comes to AI inference. So at SambaNova, the company's been around since 2017. They've pioneered what they've called an RDU. So an RDU stands for Reconfigurable Data Flow Unit. So it's very different architecturally than a GPU, and we'll talk a little bit more about that in a second. And this is our 4th generation chip, which is the SN40L. And being designed for AI allows us to do things that you can't really do with GPUs. And it allows you to have a lot more efficiency than what you get from the GPU paradigm. And to dive into a little bit more detail, I just kind of wanted to paint this picture here of like how GPUs works versus how RDUs work. So a couple things I like to talk about right off the bat, just from an architectural perspective, is one, these large language models have a ton of memory and need a ton of memory to be able to run. And having a lot of that on chip is extremely helpful for a wide range of use cases, whether that's running these chips really fast in certain types of memory. So like there are 3 different types of memory, if I just go back to the previous slide. So there's SRAM, there's HBM, and DDR. Each of them have pros and cons in terms of kind of the speed and efficiency that you get when running these different models, and you want to use them very smartly and intelligently at different points of the time when you're running these models. So with our chips, we actually have a very unique 3-tier memory architecture that allows us to optimally use the different sets of the memory that you have on chip to run these models. The other thing that really helps kind of from an architectural standpoint is, so if you look at the GPU paradigm, the way that it works when running, let's say, the base transformer model, which is what really kind of kicked off this AI revolution, is there's a bunch of different matrix multiplications and a bunch of different data that needs to get run through various different operations. And every time you need to run one of these many matrix multiplications or different applications in math for the model, you have to go to the GPU, you dump a bunch of data, you have to go back to memory to fetch the new set of data, run that through the GPU, and then there's a bunch of back and forth that ends up happening in the CPU-GPU paradigm. What that typically means is that you have kind of low operator fusion and a lot of lower local data locality when it comes to really efficiently processing the pipeline of data running through these AI models. Where the data flow name comes from in the RDU and how we've kind of architected the chip is having all of these matrix multiplications all run on chip and then have them segmented in different parts so that the data can flow from one operation to the next, to the next, to the next, to the next. And so you're not having this dance back and forth between the CPU and GPU that you would typically have. And everything can run a lot faster and a lot more efficiently on that chip. What that ultimately translates then into is a much more bigger savings in terms of the energy consumption. So if you see kind of what's happening in the headlines today is people are building gigawatt token factories. Or AI factories is another common term that comes out there. They're using gigawatts of data, and that's because at the rack level, which is basically the server that ultimately gets deployed into the data center, for the Blackwell series, you're running at 120 kilowatts at peak consumption. When you look at the Rubin next generation, so not what's currently available in the market today, but a year from now is their Vera Rubins, those are going to be 600 kilowatts. So what's happening is because of a lot of these inefficiencies at that chip level, you're translating into higher and higher power requirements that are required for AI and required for us to get to those next levels of AI. And it's purely because you have a hardware inefficiency problem. When you look at doing a completely different architecture, like the RDUs, you get to a power profile, especially in the inferencing use cases, averaging 10 kilowatts. So you'll see it kind of in that band. And the beauty of it is that they run extremely fast too. It's not like you're using less power and you're getting less performance out of it. What you actually end up finding is when you're measuring energy, which is measured in joules, it's power times time. And this is actually a much more important metric when it comes to actually figuring out how much energy is getting consumed. You'll see watts reported a lot, right? Gigawatt factories, megawatt factories, et cetera. But it's actually the energy that you use, which is purely the power times time. And in that report, that when we talked about intelligence per watt, they also introduced a new metric called intelligence per joule. And I think that, in my opinion, that's a much more valuable metric for measuring the amount of energy that's actually consumed. Because if you're taking a lot less time to complete a task, that means that you're using the power and resources way more efficiently than any other system that might be utilizing and trying to complete that task. And what they found in that report is that actually with the SalmonNova systems, it's not just the power that was significantly lower. It's more importantly, in my opinion, more impressive that it's taking less time to complete a lot of tasks, which translates to a 4x energy efficiency, even compared to the Blackwells. And so these are concepts that I think there's a lot of confusion about in the market right now, like what's energy, what's power, and I think it's very clear that having a complete understanding of what's happening even at that energy level is what's going to be needed in that next wave moving into 2026 as we're talking about efficiency. And just for reference, so at SalmonNova we have our own cloud product. It runs a wide range of these open source models that are out there today, whether that's the Llama models from Meta, whether that's OpenAI's GPT-OSS model, or even some of the Chinese models like DeepSeek. And what we're seeing is that our speeds, when you go and independently benchmark these things on artificial analysis, are significantly better. And that is what ultimately translates to a lot of that energy savings that you end up seeing out of this architecture. And these are some of the many reasons why efficiency really becomes a really key and important theme as we're thinking and looking at 2026. So now talking about agents, right? So we've spent a lot of time talking about kind of the chips and what you can kind of do from an efficiency perspective. But when you're talking about performance and moving away kind of from the energy metrics, when we think about agents and why does speed and any of this actually matter, it's when you're starting to think about building agents that need multiple different LLM calls and different models that they're working on and chaining these requests together. Each and every time you go back and forth to the data center, it introduces a lot of latency. And if each request in and of itself is taking a long time, the end result of what your agentic application will result in is going to be very slow. This is one of the reasons why when you look at a lot of deep research tools that are out there, when they're constantly thinking in the background, sometimes that takes minutes, and oftentimes a lot of these deep research tools will have to go out for hours or at least half an hour to generate your report. And that's because it's doing a lot of this back and forth in the background, calling different requests, processing, analyzing, refining. But imagine if you could have each of these requests that are kind of in this sequential chain happen significantly faster. That's why speed ultimately matters in a lot of these agentic app applications and use cases. If you can take things that would take minutes and bring that down to seconds, that unlocks a very different iterative process for coding. It unlocks a different process for creative writing, et cetera, et cetera. There are a bunch of different, whatever the use cases are that you're thinking about using AI for, that's how you get to that next level with a lot of these agents. So just to conceptualize that, right? So today, a lot of kind of the use cases that we see in the market are really around these kind of chatbot use cases. In the enterprise, you'll see a lot of different knowledge assistant-based use cases, and we're getting into that process of chain of thought where these models are thinking quite a bit. But when you really get into agentic use cases, it's calling out to a bunch of different tools. It's calling out to various different models to make those requests for you. And the tokens that you need to actually get to the end-to-end result that you actually care about are going up to an order of magnitude of 100x compared to what you've typically got when you just go to ChatGPT and write a request. And that's the level of scale that's really causing us to really think more critically about efficiency too. It's not just about the fact that it's just kind of one back and forth to the model. It's that to build a lot of these agents and agentic applications, you're going to need a chain of things that are happening in the background to fulfill the requests that you need. But that's expounding the amount of demand and that we need on the back end to actually support all of these agentic workloads that are delivering actual value. So if we're to break that down even further, right? So what is an agent, and what do we look at when we're talking about agentic applications? So for us, the way we think about agents, because I know that the market there's a wide range of definitions out there, is you tell this agent kind of the same way that you would a human, a task, and it is able to go out and successfully complete that task on your behalf. Whether that task is writing you a report that you need to give to your boss, whether that report is generating some piece of code for whatever you're building, your goal is to give that an input. Then it's going to, just the same way as a human does, go through, think about, plan what it needs to do, execute by calling a bunch of different tools that it needs to use to actually complete the task. And then this is kind of the optional step, is ideally you kind of have that feedback and learning and iteration mode that then improves it for the next task, right? So very similarly, I think that the easiest way to think about it is, if I were to give this small task to one of my employees, what would that be, and what's that bite-sized thing that I need this code that's now an AI agent for it to run and do? And the goal is not necessarily for you to go back and forth prompting this thing a bunch to actually make something happen, but it's actually more about just giving that task and letting it run. And then this is just kind of an example breaking that down a little bit, right? So again, like in this case, it's like analyze my CSV. So like if this was kind of a data analysis use case, it's going to go in, it's going to generate the code that it needs to run it. We have a great demo that I'll show in a little bit, assuming the internet cooperates with me, where you'll have our agent demo. It takes that request. It then goes ahead, generates some code. It'll be able to execute that code with our partner Daytona, which is a coding sandbox environment, so you can securely and safely run code, and then formats that end result and spits it back out to you. And it's in doing that, it's really then taking, instead of you just going to an LLM, asking it for information and getting back a result, it's now getting you into that motion of turning those thoughts that you had and actually executing and actioning on it. And that's the critical thing that we see the industry starting to move towards as that next wave to really improve the efficiency of these AI models and really deliver a lot more intelligence and results from these models and workloads. These are just some of the examples that we've started to see people use our agents demo for, whether that's in data analysis, financial analysis, coding, some of the many ones that I've talked about already. I think there's a lot of interesting things. I think scientific computing is it's very early, I think, but I think you'll start to see a lot of people in the market today starting to think about, well, what could that next level of innovation be if these models actually figure out how to solve new problems that humans haven't even solved before, or create more value from business intelligence, or even to predict and manage my portfolio of stocks. There's a lot of things here that agents are really gearing up to improve upon, and it's going to. The key here is that agents are actually improving the amount of intelligence that you actually end up getting out of these systems by chaining these prompts together and using them in effective, efficient manners. So, like I said, there's a lot more efficiency gains that you can really have with agents. Our engineering team just put out a blog on, is it LLMs that are actually solving these software problems or agents that are actually doing it? And maybe not a shocker is that if you try to throw a bunch of context at an LLM, it's largely going to break. While they can handle volumes and volumes of text into the model, what typically ends up happening when you do kind of these big shot prompts is it ends up hallucinating a lot more than if you actually have an agentic task where you've broken down the problem, and more specifically, the agent also breaks down the problem for you and then starts executing on it. You tend to get to a much better form of accuracy. The other area of research that our engineering team put out, I believe 3 weeks ago, and more as kind of a sneak preview here for this team, they're actually open sourcing some of that code tomorrow, is around agentic context engineering. So instead of kind of taking kind of these fine-tuned models and then going back to that point on kind of that feedback and iterative learning loop, what they've put together is this framework where you have a generator that helps you to improve the playbook of how that agent works. So if you think about these LLMs and kind of the system prompts that they have at their disposal, what they found in their research is that when you kind of do kind of a naive version of basic feedback, where you take a task, you ask it to reflect on that task, and then update its system prompt, it ends up reducing the performance quite considerably in terms of the accuracy that the agent actually ends up producing. So with the framework they ended up producing, which they call ACE, Agentic Context Engineering, you can actually improve with a few more steps in that learning process with a generator, a reflector, and a curator to actually improve the accuracy and improve the overall performance of the agent as it's continually learning and working with the environment, and creating what they call like a context playbook. So there's so much more intelligence efficiency that we're able to get at that agents layer, at the chips layer. And so that's really why I do strongly believe that 2026 is going to be that year where it's really thinking about efficiency and improving everything up and down the stack to really get the most out of these models that we have in the market today. So I'm happy to jump into demos. I'm happy to take questions at this time. But I do want to pause here. This is our website at Summon.ai, so you can take a look at and learn more about kind of the chip and our hardware, and also our cloud, and see some of the value out of that. I will jump into demos, but I do want to pause in case there's any questions here that I can help answer beforehand.
So you talked about speed, inference speed, how fast it is. Do you have like numbers comparing to Blackwell, like pre-fill and generation? What you can share?
Some of that information is in that paper. I don't have them off the top of my head, but yeah, they're included in kind of the paper and some of the research reports that we put out there. Yeah.
Which paper is that you're referencing?
So that's the intelligence per watt paper. Yeah.
So God knows if you can tell us you can use 10 times less electricity, climate change will be happy to hear that news. But having said that, if all the capabilities of models are converging to a single point, I think, with the new exciting use with post-process reinforcement learning methods, that's the way you're going to be able to distinguish yourself from your competitor. Are you guys fully integrated with PyTorch? I didn't see, Sanvanova at this year's PyTorch.
Yeah.
And if not, are you going to introduce yet another MLIR dialect? How are you going to be able to make full use of your hardware without having to yet learn another language for kernel development?
No, that's a great question. So right now, when we release models, it's our engineering team that's kind of working with at the compiler level and at the PyTorch level to take these models and run that on our hardware. It's on the roadmap right now to kind of expose that and make that a lot more easier. But some of that is also getting a lot of those chips more accessible into the ecosystem and also into some of the research labs there as well. So that's something you should expect to see kind of moving into the next year. We don't have those live just yet. So what we typically do, especially because this is just how the market's working, right, is a lot of these models are open source anyway. So it's really easy for our team to go in and optimize them. And even that's true in the GPU ecosystem today, is that what you get kind of base out of the GPU is quite slow and very inefficient. There are a lot of teams and labs that are going in and going in and improving that. So right now it's really kind of at our team, and then in kind of the future iterations that we're planning to release in the future, we'll make those a lot more accessible. I don't have kind of the details on how they want to expose that right now, but that is coming, and we know that that's absolutely critical for the ecosystem.
Why don't we jump into the demo for time's sake?
Awesome. So I mentioned that agents demo. Let me make sure that it seems like we're up and running. So This is available at chat.samanova.ai, and this is a open source, easy to use tool for really anyone, and it's kind of our deep research playground. So one of the things that I was kind of testing and iterating was like, get me, let me actually put this here. There we go. All right, cool. Get me the top routes for airlines for Thanksgiving. So very simple request. Most of the kind of the chat demos that you see out there will be able to kind of go to the internet, find that information, and then be able to generate that for you. So we'll give that a second here just for the internet to come through. We can see kind of the bunch of those different routes that are here. Now let's say I actually want to go ahead and visualize this as kind of an HTML page. So generate a HTML page that has a map of the top domestic. So like we talked about in that slide where we talked about generating some of the code and then going through and actually taking what you had and turning it into an action. This is where agents are actually making multiple calls on your behalf. And what you can see here right now is that it realizes in that sandbox, it actually needs a dependency. So it'll go and install that dependency, kind of a map to help you visualize the list of kind of these top routes that flights are taking for the holidays. So if we go back, once this finishes here, actually I can just stop that here. And you can kind of see, compared to a lot of other use cases, it's running insanely fast, and we'll see that a little bit more in the cloud. If we go up to the top here, so this is kind of a pretty simple example where it's going out to the internet and fetching some data. Let me see if I can make that a little bit bigger. Yeah, that looks a little bit better, right? So it's using kind of about 9,000 odd tokens here. It's only outputting kind of a handful here, and then it's generating kind of a couple LLM requests to go and make the when we go scroll down, you can see kind of the amount of input starts to slowly ramp up as it's generating and creating a lot of the code that's required for it to generate that end report. And then it's going out, also has to call various different tools here to actually run the code, then be able to actually help you visualize it here on a map. So this is where kind of the tokens start to expound when you're looking at a lot of these agent use cases compared to kind of just simply going back and forth and talking to a prompt in a model, which maybe takes on the magnitude of like hundreds of tokens. Now we're talking about tens of thousands of tokens here. This is all purely powered by Samanova and our cloud, running on our hardware in the back end. So if you head to cloud.samanova.ai, and this is also linked on our website, you can see the dashboard of our cloud. You can play around with a bunch of these different models here. So this is the model that we're actually using, which is the DeepSeek V3 model. If I give it kind of a very quick prompt like write a binary search tree, it's going to be able to do that, and it's going to be doing that really fast compared to what you would typically get out of the GPUs. So any of these models are available for developers to start building and playing and iterating with. You can create API keys and take a look at any of the pricing and billing metrics that are available here on our site today. That's all public, and this is really designed to be kind of that place where developers can start to take advantage of our models and capabilities. To your point earlier, these models are built by our team, right? So they take the open source code, they optimize that with kind of our internal tools. Once we make that more accessible out into the open, then the goal would be for the ecosystem to really be able to help optimize and run these models on that hardware and get a lot more of those energy efficiency gains that you were just talking about. I think I'm at time, so if there's any other questions, I can take one more. Otherwise, thank you so much.